In 1925, David Hilbert tasked his followers with proving infinitistic mathematics is finitistically reducible and therefore trustworthy. Infinitistic mathematics deals with the infinite or never-ending mathematical objects while assuming they exist, whereas finitistic mathematics does not evoke the concept of infinity. It only deals with actual numbers. Later, Kurt Gödel proved that no system of logical axioms can ever prove its own consistency. To prove that a system of logic is consistent, you always need another axiom outside of the system. This means there is no ultimate set of axioms, no theory of everything in mathematics. Gödel's theorem meant that Hilbert's dream could have been shattered. The axioms of finitistic mathematics cannot even prove their own consistency, let alone the consistency of set theory and the mathematics of the infinite. Nevertheless, mathematicians came up with infinitistic proofs of concrete statements about natural numbers, theorems that had applications in physics and computer science. Imagine you have an infinite number of points in a plane. Pair every point with every other point there is. Now color every pair with a finite number of colors according to some rule. When this is done, Ramsey's theorem for pairs asserts that there will exist an infinite monochromatic subset, a set consisting of infinite points, where all possible connections are of the same color. The thing is, the same idea works if you have a finite number of points instead. With a minimum of 6 points, you will be able to create a monochromatic polygon within the finite graph. This means this theorem is finitistically reducible, as in it works with both finite and infinite structures. Imagine you connected and colored 3 points instead of 2. Ramsey's theorem for triples asserts that within this infinite set, there exists an infinite monochromatic subset whose every connection of 3 points has the same color. This theorem, however, is not finitistically reducible. If you take a finite number of points, Ramsey's theorem for triples is not guaranteed to work. This idea, as many put it, bridges the finite-infinite divide, separating finitistic statements from unfinitistic ones. Ramsey's theorems somewhat allow us to draw the line between the finite and infinite, where Ramsey's theorem for pairs represents the finite and Ramsey's theorem for triples the infinite.
Constructing the finite with infinitistic building blocks seems possible. We may even find a more suitable boundary between the finite and infinite. Now, it is our turn to share Hilbert's dream and push the limits of our understanding to infinity and beyond.